record here. Okay. Hi, hello. Welcome to section number 1. My name is Colton. You guys have probably heard from me via email or announcement. I'm going to be your TA for the fall for organic chemistry. I really like teaching organic chemistry with Harvard. I've been doing it for like 7 years. And I haven't done this exact course, so there are some things that are like a little bit different from the ways that I presented in the past. But I'm excited to go on this journey with y'all. Organic chemistry is a lot, and so I try to do what I can to make it a little bit easier for y'all. Um, with sections, so there's a section handout on Canvas that essentially has 6 questions to go over in section and work through them. And that's most of like what the kind of required section materials are. But because I'm used to like teaching this and have kind of other resources built out for like all of the different like lessons for organic chemistry, I think it's helpful to use some of that and to kind of intersperse it with the questions so that there's a little bit of the review info as well. Um, and then, ooh, my iPad's frozen. Let me try restarting it real quick. But yes, I would say either have a copy of those blank questions on hand or have the section notes that I posted that integrate the questions into the handout. Okay, let's see about this. Okay, she is moving and grooving. So, if you haven't already, please take a minute and just scan the QR code for attendance things for today. Attendance is not required, but I do just like to kind of keep track of who's coming and showing up and everything. The first page of the section notes, it essentially has an outline of the lecture material because I know we cover a lot in a 3-hour lecture. There are many, many pages. And so I think it's nice to just kind of see organizationally what are the big ideas. I also sometimes put some memes and some like skills to develop from the lecture. And then there's another QR code at the bottom, which is for any like feedback of things that you thought worked well or didn't work well for section. And so that will be on all the section notes. But we have kind of 6 big things to cover today. The first 2 are kind of review of Gen Chem things with some basic scales and resonance. Then we're going to talk a little bit about nomenclature and functional groups, and then we'll end off with the newest stuff of conformational analysis and MO theory. So I'm going to go ahead and jump in then. And I want to make sure I have the chat open if people have like questions as we're going. Also, feel free to like stop me and like just unmute yourself and say something if I'm ever like plowing ahead and you're like, whoa, whoa, whoa. Cool. Okay, here we are. So, with Gen Chem review, and like any kind of review lecture or review topic, it's pedagogically horrible because for people who don't know it, it's like going far too fast, and for people who know it, it's far too slow. So we'll try to strike a balance. But really what I want to do is kind of a rebranding of some things that you've seen in Gen Chem. So first off, we have formal charge. In Gen Chem, you got really comfortable with this formula of the number of valence electrons minus the lone pair electrons minus the number of bonds. And you might have seen it in a slightly different form, but this is essentially it. We don't want you to be having to do math every time you're seeing molecules in organic chemistry. And so essentially we want you to start getting to where this is a passive visual skill, to where you can see an atom, see how many bonds it has, and you're like, I know that carbon with 4 bonds, neutral. I know that oxygen with 2 bonds is neutral. But if oxygen has 3 bonds, she's angry, she has a positive charge like H3O+, and if oxygen only has 1, then it's negative like OH-. So I would just encourage you to kind of think about this as a visual skill to develop. And in doing that, can we try like a quick practice? So I'm going to try having y'all like put in the chat. But here are 2 molecules where formal charges have not been given to us. So what is the formal charge on this carbon? Carbon number 1, I'll label it. dong. Thank y'all for responding. Great. We see carbon. She has 4 bonds. She's happy. She's content. What about this carbon number 2 over here? Very nice, very nice. Again, triple bonds, that's 3 bonds and a 4th bond on the other side. But then finally, carbon 3 over here, she only has 3 bonds. So we know that she's unhappy, and then we just have to check, does she have a lone pair or not? Since she has a lone pair, she is going to get a negative charge over here. So these two are neutral, the one on the end is negative. Then, for the oxygens, we're going to do the same kind of process here. So this oxygen on the right has 2 bonds, and we know oxygen's happy with 2 bonds. So we know that that's neutral. This one in the middle, the oxygen has 3 bonds. So we know that it's going to be positively charged. And the one on the end has 1 bond, so negatively charged. So again, it'll just kind of be like speeding up these skills that you already had mathematically from Gen Chem. Moving on, talking a little bit about skeletal structures. So if you've seen other like chemistry classes, oftentimes they will write things out like CH3, CH2, CH2, CH, CH2, CH3, CH3. This is called condensed notation. It's just obnoxious. It takes way too much time. And organic chemistry, like organic chemists, I should say, are fundamentally lazy. We want to do things in as little time as possible. And so we developed this shorthand for representing chemical structures called skeletal structures. And essentially, it assumes that carbon and hydrogen are the skeleton of our molecule, as is the case for most organic compounds. So the way it works is every unlabeled end or bend is a carbon, and we are going to imply all carbon-hydrogen bonds. Now, lone pairs we generally do not put on the molecule unless we are going to use it for like a reaction or something, so you don't need to worry about including lone pairs. But formal charges do have to be explicit. So if you have a skeletal structure, you should be looking for formal charge as like a final check each time. And then the last kind of like warning here is any atom that's not carbon, we call a heteroatom. It's different from the carbon-hydrogen like backbone. You do have to explicitly draw any hydrogens on it. So like if we had something with like a nitrogen on it, we couldn't just not write the hydrogens and like be like, oh, they're implied. We would have to explicitly write any hydrogens attached to it. So with this, we see this is an unlabeled end, so we know that that's a carbon, and we know that its formal charge is 0, right? Because any formal charge would have to be explicitly listed. So carbon with a 0 formal charge, how many bonds should it have? Can you put in the chat? Carbon with a 0 formal charge, how many bonds does she have? Yeah, 4. So because we've only listed 1 bond that we can see down here, how many hydrogens must we have on this carbon? Ding dong. Okay, thank y'all. 3, exactly. And so that's going to be kind of the secret sauce here. So like similarly, this carbon on the end, we know it's neutral and it only has 1 bond present, so we know that there are 3 hydrogens on here. How many hydrogens are on this carbon? She already has the 4 bonds on here. So she couldn't have a secret 5th bond even if she wanted to. Octet rule holds strong for carbon, so we can't have more than 4 bonds. So she doesn't have any hydrogens. And then the last one is this carbon here. So how many hydrogens are on this carbon? Well, we see 3 bonds, so it might be tempting to say there's 1 hydrogen that's missing. It might be tempting, but we know that she has a positive formal charge. And carbon with a positive formal charge over here, we see is only 3 bonds. There's no like hydrogen or additional bond present. So there are no hydrogens on this one. Likewise, over here, we see a carbon that has 2 bonds, so we know it must have 2 hydrogens if it's neutral. And we see that the hydrogen on this molecule, on this oxygen, has to be explicitly written. Lastly, if we have something like a name like heptane, we use the parent change hepta for 7 here to tell us how many carbons that we have. And then doing a skeletal structure is super easy from there. We just do 1, 2, 3, 4, 5, 6, 7. So counting and making sure that all of our bins and ends together add up to 7. Versus writing CH3, CH2, 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 and so forth. Similarly over here for 2-hydroxypentane, we would draw a 5 carbon, 1, 2, 3, 4, 5 carbons. We'd pick one side to start numbering, 1, 2, 3, 4, 5. And if we are drawing it, we don't care about which way we number. Like, we are God in this moment. And so we can pick, hey, I'm going to start numbering it this way. This is what I'm making carbon to. And then you can put your hydroxy over here. If you did it the other way and like numbered from the other side and put it over here, that's exactly the same and totally fine. So that is skeletal structures. We're going to do some practice on this. The way it generally works is I'll do a little talking review, then we'll do practice. Talking review, practice kind of trade off. But the last little talky review before we get into the practice is hybridization. So does anyone know the like quintessential DS game Cooking Mama? Is that part of y'all's vernacular? Okay, I see some faces. So I imagine hybridization like Cooking Mama with her pot on the stove, and the ingredients are orbitals. We have these atomic orbitals of 3 p orbitals and 1 s orbital. And if we want to hybridize them, we put all the orbitals in the pot, mix them around, and they come out as 4 sp3 hybridized orbitals. The big thing is, however many atomic orbitals you start off with, which is 4 always, you're going to come out of it with 4 total orbitals after hybridization. So if you put in 4 atomic orbitals, you get out 4 sp3 orbitals. But what if you want to keep one of your p orbitals pure, and you only want to hybridize 1 s and 2 p orbitals? Well, then you Cooking Mama throw those in the pot, but keep that other p orbital out on the counter. You stir the pot, you get out 3 sp2 orbitals, because that's how many you put in, and then you still have that p orbital that you did not hybridize that is there. And then same analogously for sp. Now, this hybridization is helpful because it corresponds to the geometry of molecules. When you have an sp3 hybridization, it's going to adopt a tetrahedral geometry like this. And this is just like maximally the way to spread out 4 things in space as much as possible, like just a symmetry thing. Then for sp2 hybridized, you are trigonal planar. So you have these 3 in a plane. And then your p orbital, whenever you have a p orbital, it's going to be exactly like perpendicular to the plane of the other orbitals. Then finally for sp, you have this linear organization of the sp orbitals. And then you have 1 p orbital that's perpendicular, kind of going up and down, and then 1 that's perpendicular going into and out of the page. That's always a little bit trickier to show. But the easy way to kind of do hybridization, if you're looking at a molecule and you're trying to figure out what's the hybridization of the different atoms, is counting the number of electron domains. And electron domains is a bond of any type, single, double, or triple bond. If it's a double bond, it still counts as 1 electron domain. And then lone pairs also count as an electron domain. And your number of electron domains is going to determine what your hybridization is. If you have 4 electron domains, you're sp3 hybridized, so you're tetrahedral, 3 sp2 hybridized trigonal planar, 2 sp hybridized and linear. So with that, we're going to go into this first practice on the skeletal structures. And first, what we're going to do is convert the skeletal structure into a full Lewis structure. So we are going to do the annoying exercise of drawing out all of our carbons and hydrogens and everything. So to start this, let's just get a skeleton like backbone of everything. We know every unlabeled end and bend is a carbon. So let me start by drawing all of those carbons in. We have a carbon, carbon, oxygen, carbon, carbon. That okay so far? Okay, I'm going to keep my positive charge here. And then I need to start filling in hydrogens. So all of these carbons are neutral, and we know carbon likes to have 4 bonds. So each of these 3 on the end, we are going to add 3 hydrogens to. So we have H, 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 and one more time on the right. And then this carbon is exactly like the one that we saw over here, where this carbon has 3 bonds and a positive charge, and so it doesn't have any hydrogens on it. So it is just good as is. And then it also wants us, for this specific Lewis structure, to draw in lone pairs. So our only girly that has some lone pairs is going to be oxygen here. And oxygen in its neutral state likes to have 2 bonds and 2 lone pairs. So let's just draw in those 2 lone pairs here. And with that, I think that we have the full Lewis structure. So the second part of this is to give the hybridization and the electron geometry of each atom. And we're going to do the non-hydrogen atoms because hydrogens are just kind of boring. Like, they're always on the end. They're always just an s orbital. So we start off, let's look at these 3 carbons, because we know these carbons look almost exactly the same. They're a CH3 at the end of the molecule. Each of these carbons has 4 bonds, and so it has 4 electron domains. So using our master table up here, if we have 4 electron domains, we are sp3 hybridized. So we have that this is sp3 hybridized. Likewise, for all of these other terminal ones, all the ones in the end, the carbon has 4 electron domains, like 4 different bonds, and so it's sp3 hybridized. What about this carbon right here? How many electron domains does it have in the chat? And then, given how many electron domains, what hybridization are you thinking? Ding dong. Very nice. So she has 3 electron domains or 3 bonds, and so we know it's going to be sp2 hybridized. And one thing that's kind of helpful to think about is when we have a positive charge, we literally have a lack of electrons, and electrons go in orbitals, right? So when we have a positive charge on this carbon and we don't have a full octet, we actually are going to have an empty orbital. So there's just an empty p orbital on this carbon, and then all 3 of these bonds use the 3 sp2 orbitals. So that's one way to think about how this hybridization relates to like the actual electrons on here. Are things that have electrons, these 3 bonds, we want to spread out as much as possible. So we're thinking trigonal planar to spread 3 things out as much as possible. That's our sp2 hybridization. But then we know if we are sp2 hybridized, we have 1 p orbital left over. And so that p orbital is just going to be an empty p orbital on the carbon. Then the last one here is this oxygen. So how many electron domains does it have? Also, Gabrielle, I love that you are answering every question correctly, but then putting a question mark after it. Like, maybe? Maybe? So we have 2 bonds, but remember, lone pairs also count as electron domains. So 1, 2, 3, 4 total electron domains. So we see this, we expect sp3, but there is drama, there is mystery, there is intrigue afoot. If I was in your shoes, using all the tools I've seen before, especially Gen Chem, I'd be like sp3, but it's not. But it's not. And the reason it's not is because of resonance, which is what we're about to talk about. So we're going to come back to her, but there is one exception to this table, and it has to do with resonance. So the last thing is it just says to list the geometries, which I forgot to do when I was doing all this. So this is tetrahedral, this is tetrahedral, this is tetrahedral for our sp3s, and then for sp2, it's trigonal planar. And then this shocking upset we will come back to. So let's figure out what's going on with Miss Resonance and then see how that enters the picture here. So, again, everyone comes into organic chemistry with a different understanding of what resonance is, and a lot of times what resonance looks like in Gen Chem is saying that like there are 2 Lewis structures and it's just like a way of redrawing it. But we are going to want y'all to think a little bit more kind of critically about like what actually is it, why is it there, and like why is it such a big factor that we have to keep track of. So the classic example is like benzene. So benzene alternates in the Lewis structure, single and double bonds. But we know from Gen Chem that single bonds are longer and double bonds are shorter. So chemists for a long time were like, oh, she's this weird, like, hee-haw, kind of like long, short bonds around a six-membered ring for benzene. But then when they finally developed tools where they could actually measure the bond length of benzene, they saw that the actual bond length was the same for every bond, and it was somewhere between a double bond and single bond in length. And so resonance comes from essentially a failure of our notation. So our notation of Lewis structures is really, really great for most bonding that we have seen up until this point, and actually just like, it's a great tool, but it fails to capture the actual bonding in some molecules. And so we have to use two Lewis structures to represent what the actual bonding is. So in this example, like, there is a double bond here in one of the structures, and there's a single bond here in one of the structures. And the reality is, it's somewhere between a double and single bond. So this is kind of like saying the real thing that exists is a rhino, and it's kind of like a resonance hybrid between resonance structures of a unicorn and a dragon. The unicorn and the dragon don't actually exist, depending on who you ask. But the thing that's kind of a weird hybrid of them is the thing that is in reality. So we are trying to describe the rhino by drawing these things that are not the exact structure, but give us kind of glimpses of what the real structure looks like. And we call the real structure a hybrid. So what is causing this? Resonance is caused by electron delocalization. And delocalization is just the idea that electrons like to spread out. Like, they are negatively charged, so they want to repel each other. And so normally, if you have it in a bond, you know, it's doing okay. But if she can spread out among multiple nuclei, multiple like positively charged nuclei, it's actually going to be a really stabilizing effect for molecules. And there's one kind of key thing that needs to happen in order for the electrons to delocalize and kind of spread out among a bunch of atoms. And the electrons have to be in a p orbital in order for delocalization to happen. So if we are thinking about like our normal sigma bonds can be between like sp3 or sp2 or sp or whatever, but these are always going to be between the nuclei. And so these electrons can't spread out without literally bumping into a nucleus. Whereas when our electrons are in p orbitals, these p orbitals and like pi bonds, they have side-by-side overlap of the orbitals, and there is nothing in this space to stop the electrons from just spreading out and like going over to their friend's house. And so when our electrons are in p orbitals, they can delocalize and spread out and get that stabilization. Are these, can I get like thumbs up, thumbs down? Are these ideas that you're like, ah, yes, I've seen that, that feels okay? Or like, if you're like, what was going on was the strange magic. Okay, I'm getting like moderate feedback of like, this is not super crazy. So I will take that. Indeed. Another key idea here is that when we have different resonance structures, not all resonance structures are created equal. Some resonance structures are going to give us a better idea of the actual bonding of a molecule than others, and it really depends on the stability of the resonance structure. So let's look at these two resonance structures for a molecule right here. The top one or the bottom one, which do you think is more stable? And maybe in the chat, yeah. Gosh, it's been so long since I've done Zoom teaching, and like it's throwing me back truly to like the throes of 2020, 2021. So it's a weird time, but I appreciate y'all. Yeah, the top one. So the top one doesn't have any charges, the bottom one has charges. And so because this top structure is more stable, it's giving us a more accurate representation of what the actual bonding is looking like. Like, the actual bonding in this molecule is not going to have this weird dipole where there's like a negative over here and a positive over here. It's really going to be more evenly spread out. So that's the idea that like our more stable resonance structures give us a better idea of the actual bonding of the molecule. So how to be more stable? Have complete octets, have as few formal charges as possible, and then if you have to have a charge no matter what, put your charges on more electronegative atoms for negative charges, and put your positive charges on less electronegative atoms. So for example, if I had a resonance structure where I had a negative charge on O, versus I have a structure where I have a negative charge on carbon, who's more electronegative, carbon or oxygen? Well, oxygen. Oxygen's super electronegative in our periodic trend top and to the right. It's, I think, our second or third most electronegative element. So this negative charge, if it has to be on some atom, it's going to be more stable on a more electronegative atom, something that likes holding on to those electrons. So I know that there's a lot of information. Yes, Evan, there's a question.
Is the implication here that all of these legal structures like exist to some extent, but like in vanishingly small quantities at the bad structures, or is it that those bad structures never happen?
So, great question. And the answer is kind of like, that's the wrong question in some senses. And it's good to bring it up because it's not that this molecule is sometimes like this and sometimes like this. This molecule is just doing its own thing and it's always the same all the time. It's just about our representations of it as a Lewis structure. And so if we can draw it multiple ways, like the snapshot, all of these are giving little snapshots of how the real bonding might be. And the snapshots that are more important are the more stable resonance structures, if that makes sense. So it's not like interconverting between them. It's just different like pictures that we can draw with our notation. Yeah, but thank you for asking. Yeah.
Thank you.
Totally. So there are some basic rules for drawing resonance structures. One, you can't just poof away electrons. You can't just add electrons. So the number of valence electrons need to stay the same the whole time. Two, you're not going to be breaking any single bonds. Remember, resonance, we said, only involves like p orbitals. So p orbital things are either like lone pairs, empty orbitals, like we saw the positive charge on the carbon, there was an empty p orbital, or pi bonds. So those are all the things that are going to be changing. So all of your single bond structure is going to be exactly the same. And then the last thing is that the hybridization of all atoms must stay the same between resonance structures. And again, this comes from the idea that it's not actually shifting between two states, it's only one state. And so if one of its states is a different hybridization than the other, or it looks to be a different hybridization than the other, then we know there's actually something off with our understanding of its hybridization, because its hybridization is only going to be one thing the entire time. And that's what we're going to come back to with the exercise. So that's kind of the key thing. But last tool before we actually jump into the exercise and get to practice some of these resonance ideas. So curved arrows, organic chemistry. Chemistry, we have a lot of arrows. But curved arrows are really going to be our language for like what is up with molecules in organic chemistry. Curved arrows for organic chemistry show the movement of electrons. And we have to be really specific with how we draw these arrows because we're essentially making arguments for how electrons are moving. So we have this, which is called a double fishhook arrow, which shows the movement of two electrons. If you go on and take the next semester of chemistry, or I think actually even later in this course, but not for like several weeks, so don't worry about it. If you only drew it with like one little head here, that would be the movement of one electron. So that's why I was just saying, like, make sure you have a double edge on here to be really specific. And these curved arrows are different from like equilibrium arrows, reaction arrows. You might see this big blocky arrow, which is about thinking backwards in logic. And then this is the resonance arrow, which tells us that two structures are resonance structures. So we place this one between two Lewis structures to say, hey, these two things are resonance structures for each other. But curved arrows are going to tell us how we get from one resonance structure to another resonance structure. So there are three valid moves that we can do curved arrow-wise for resonance. We can start with a pi bond and take the two electrons in the pi bond and move them onto an atom and make them a lone pair. And when we do that, think about this carbon over here. This carbon was satisfying some of its octet from the two electrons that were in this pi bond, but now those two electrons are over here, so we robbed her. So she is missing electrons. She has a positive charge. And then this carbon over here, where we've added the lone pair electrons all on that one carbon, that has a negative charge now. because remember there is a sneaky hydrogen over here. So this has a sneaky hydrogen that's going to be 3 bonds and a lone pair on a carbon, so she's going to be negative. So that's our first legal move, going from a pi bond to a lone pair. But then we can exactly undo that. So we could take electrons that are in a lone pair and move them in, and our arrow is going to go to this bond to say, hey, it's going to become a pi bond on this, between these 2 atoms. And then balance is restored. We're back to normal. The last move is really only when you have carbocations present. It is a pi bond to a pi bond. So here we're just shifting our pi bond from being over here to being on the other side. And then when we did that, we robbed this carbon. So this carbon has a positive charge now. And I've included some examples here that just kind of show some of this arrow pushing because it's pretty new, and also because you're being asked to do it on the homework. So I just wanted you to see some examples of it. But why don't we try to put this resonance stuff together with an exercise? So here, I have one. This is not on the handout, but I wanted us to give us a little bit more practice with resonance just because it can be a little tricky. And if we were tasked with drawing a resonance structure of this molecule, one of the first things that we can do is we know that we didn't disrupt any single bonds, right? Resonance is only affecting pi bonds and p orbitals. So let's just go ahead and draw the whole single bond framework for our other structure. We know all of these atoms need to be in the same spot, and they need to have the same single bonds between them. But then when I'm thinking about doing resonance and doing my curved arrows, we need to have a source of electrons. The electrons need to start somewhere. So where is there the most buildup of electrons on this molecule? And feel free to Zoom chat, or honestly, we have 8 people. Feel free to unmute. We're out here. Yeah, Evan. So the top oxygen. So she has a negative charge. She has a buildup of electrons. So what we're going to do when we're generating our resonance structure here is we are going to start at the lone pair as our source of electrons. And if we are starting with a lone pair, we only have one valid move. We can turn this lone pair into a pi bond. So in our resonance structure, I'm going to draw this in kind of blue. That is going to become a pi bond over here in our resonance structure. But there's an issue. The issue is this carbon already has 4 bonds, right? It already has a full octet. So if we are going to make another bond with this carbon, we have to break a bond. What's the only kind of bond that we can break with this carbon? Can we break this bond? No, that's a single bond. Can we break... Yeah, I'm trying to lead you to it. I think you all see. We have to break the pi bond over here. So what we're going to do is do a pi bond to a lone pair because we don't have a carbocation anywhere, so we can't do the pi bond to pi bond. So we are just going to draw an arrow from that bond over here to the side. And then that arrow and these electrons are now in the product going to be a lone pair over here. So now if we're thinking about formal charge, this oxygen at the top now, she had 2 more lone pairs, but I didn't draw it initially because we weren't using them. But now the oxygen at the top has 2 bonds, 2 lone pairs. It is neutral. But if we look at our carbon, this carbon initially over here had no formal charge on it, so we know that there's a sneaky hidden hydrogen here. And now we have a hydrogen, 2 more bonds to carbon, and a lone pair, so that's going to have a negative charge on it now. So that is kind of the difference of drawing organic chemistry versus gen chem resonance structures with these curved arrows to see where did all the electrons go, what did they become. And then the last question here is, between these 2 resonance structures, is this one in the box more stable or less stable? And to do that, we look at charges. So everything still has a complete octet, but the difference here is we have a negative charge on oxygen and a negative charge on carbon. Now, we said earlier negative charges are happier on more electronegative elements, so we know that this one over here with a negative charge on oxygen is more stable, and the one on carbon is going to be less stable. So with that in mind, returning to our past example, this structure over here that we started with last time, if we did a resonance structure for it, where is our source of electrons? It's not the most clear. It's clear where we need electrons. So like the positive charge says, hey, we need to put electrons in here somewhere and to get rid of a positive charge. So our only candidate is the lone pair on the oxygen next door. So when we draw a resonance structure, we are going to draw an arrow from the lone pair to this bond. And now we are going to have a double bond there. So formal charge-wise, we check our oxygen. She has 3 bonds now and only 1 lone pair. So she's going to have a positive formal charge. So between these left and right, he wants to take a stab at which one is more stable. Dahlia, do you want to unmute and explain why?
Yeah, I guess because we want negative charges on oxygens, like they're more electronegative, so we don't want positive charges on oxygens. Like it's kind of the same thinking.
Yeah,
Like,
you have the exact right idea, but there's one more thing that's missing in this example. Does everything have a complete octet in both versions? So, like over here, this carbon has 4 bonds, it has a full octet. Here, this oxygen has a lone pair, 3 bonds, that's 8 electrons around it, full octet. But over here, this carbon doesn't have a full octet. And so we have all these competing things for the stability. You're totally right to be looking at what's the species with the positive charge, but the thing that's going to actually be a bigger deal here is having complete octets. And because this one has complete octets, it's going to be the most stable one. That was a little bit of a trap, so I'm so sorry. Please continue to answer things. I appreciate you. But like that is the exact thing of like competing these ideas. But last thing with the hybridization. Now, if we look at this resonance structure, the one that's the most stable, how many electron domains does she have around her? Well, she has 1 with this double bond, 1 with this single bond, and 1 with this lone pair. She only has 3 electron domains, which would be an sp2 hybridization. And so, if this is the most stable resonance structure because it has complete octets, we know that this is just going to be sp2, and our hybridization can't change between our different resonance structures. So this also has to be sp2, even though it looks like it has 4 electron domains, so it should be sp3. And I've seen this in so many organic chemistry classes, and I was like, this needs better branding, just because this is not sticky for like a reason why there should be this exception. So I called her the neighbor rule. So the neighbor rule is, if you have atoms that appear to be sp3 hybridized, that are adjacent to a pi bond or an empty p orbital, and have a lone pair, then it is in fact going to be sp2 and not sp3. And so, if we look at all these examples, this oxygen has 1, 2, 3, 4 electron domains. It has a lone pair, and it is adjacent to a pi bond. And adjacent means like it is the neighbor, it is not part of the pi bond. So we do not want our pi bond to be here because then the call is coming from inside the house. Like the pi bond is on the atom with the oxygen. We want it to be firmly in the neighbor category of the pi bond. Well, we know this pi bond has p orbitals. So what it's going to do is it is, instead of hybridizing an sp3, it's going to keep one of its p orbitals pure and have a p orbital so it can do delocalization and spread out and be super stable. Same thing over here. We have this nitrogen, which has 4 electron domains, it has a lone pair. It appears to be sp3, but it's going to want to put this lone pair in a p orbital so that it can do resonance and spread out with all these other p orbitals next door. And our resonance arrows that we could draw for it would look something like this. Now, is this resonance structure a great one? Well, not really. It has two charges on it. But just the fact of having access to delocalization makes the molecule more stable, even if this snapshot's not the best representation of what it looks like. Resonance delocalization is honestly going to be the answer to like 80% of the conceptual problems that we ask you in this class, which is why I'm spending so much time on it. So maybe can we do this quick practice? I want you to take like 30 seconds. And for each of these O's and N's, I want you to tell me just what is the hybridization. And really this is a check for can you apply the neighbor rule. Don't do this second thing of this which orbital the lone pair is in, just time-wise. But take a minute and try to apply this. So with each one you're checking, does it appear to be sp3? Does it have like 4 electron domains? Does it have a lone pair? And is it adjacent to a pi bond or MTP orbital? I'll kind of give you a little time. So to start y'all off, I just put in the lone pairs. So there's no indicated formal charge, so we know that the lone pairs and all of these are implied to make them all neutral. The top one, do we appear to be sp3 hybridized? No, we only have 3 electron domains, these lone pairs and this bonding area. So this is just straight up sp2, and it's just a normal sp2. So no like neighbor rule tempting. Then this nitrogen appears to be sp3 hybridized. It has 4 electron domains. It has a lone pair. And is it adjacent to a pi bond or MTP orbital? Well, if we go to its neighbor, there's a pi bond. So, and when I say adjacent to a pi bond, I think when you see a pi bond nearby, just draw out the p orbitals of the pi bond. And if this lone pair is neighbors to a p orbital, then yes, that satisfies that third criteria for the neighbor rule. So this is actually going to be sp2 by our neighbor rule. And it's that one exception to the number of electron domains. Then last one, this molecule, oxygen over here, she appears to be sp3. She has 4 electron domains. She has a lone pair, but is she adjacent to a pi bond or an MTP orbital? No. The pi bond MTP orbital is all the way over here. So that it does not carry over. It's too far away. So this is just going to be our sp3. Then lastly, this bottom nitrogen over here, it just appears to have 3 electron domains. So it's sp2 hybridized. This top nitrogen appears to be sp3. It has a lone pair. And then it's right next door to pi bonds on both sides. And so by our neighbor rule, it's actually going to be sp2. Any questions on this neighbor rule in resonance before we move on? Yeah.
I have a question, Colton.
Totally.
So the neighbor rule only applies one time, basically, even if it has 2 MTP orbitals.
Yes.
It's not going to lower it even more.
Yes. And the reason is it has to do with the fact that p orbitals are always perpendicular to each other. So like this nitrogen on the bottom already has p orbitals doing the whole delocalization. So like they are doing this like circle little dance of electrons. They're so happy. But even if this nitrogen were to get another p orbital, that p orbital would have to be perfectly perpendicular to it. And so is that perpendicular p orbital going to be able to engage in the electron party with all the other ones that are going the same direction? No, they have to be this like parallel side by side overlap. And so the idea is kind of like, why would the atom go to the trouble of keeping another p orbital around if it's not going to be able to delocalize? And so it only really needs to keep that one p orbital around in order to like do the resonance here and have this like pi bond. Yeah, that's a great question.
Is there like a quick way to recognize when there's an empty p orbital rather than a pi bond?
So empty p orbital, there are only like 3 cases really that you will see in the class. Number 1 is a carbocation. If you have a positive charge on a carbon, that's an empty p orbital. And then 2 and 3 are both in column 3. So borons. Borons are this weird example of like, boron is neutral with like 3 bonds. But if it only has 3 bonds, it has an empty p orbital on it. And the similar one is aluminum. So aluminum with 3 bonds has an empty p orbital. So these are really the only cases that you're going to see with an empty p orbital. Yeah, totally. So the other thing that I'm going to give as a disclaimer is I am used to sections being 90 minutes. And also we are covering more content than normal in lecture 1 for my speeds. And so I'm probably going to be going like 10 minutes over. And if anyone needs to leave, totally fine. But I'd rather like make sure you have tools for all the things, especially since it's recorded and people can like watch it back. But I do not mean that as like being disrespectful of your time. I mean that as like just wanting to provide y'all with resources. So if that's okay. Okay. So moving on, very different vibe now, nomenclature and functional groups. We had zoomed in, we were all talking about atoms and the details. Now let's zoom out and talk about something really boring, naming. Nomenclature is one of my least favorite things in organic chemistry, mostly just because it involves like lots of memorization. The nice thing is we don't do a lot of nomenclature. We do like the barest of bare bones nomenclature. Other classes will sometimes spend 2 or 3 weeks on nomenclature and make sure that you know how to name every single compound, whatever. We don't care about that. But there are some basics that we do want you to know. So one is abbreviating carbons. So if we have 1 carbon on the end of a molecule like a CH3, this is a methyl. If we have 2 carbons on the end, it's an ethyl. 3 is a propyl, and 4 is a butyl. All of these names, methyl, and methane for 1 like carbon, CH4, ethyl, and ethane, propyl, propane, butyl, butane, these are just historical names. Like they were just calling these things like these names and they've stuck around. And so it unfortunately is something that you just have to memorize. And so again, this might be a generational thing. I grew up with the Disney Channel movie Camp Rock, and there's like a meme where the kids in Camp Rock are like doing this like Camp Rock, like weird dance in the forest. And I imagine like walking around meth, eth, prop, bute, meth, eth, prop, bute as just like 1, 2, 3, 4 carbons. It's really, really like smooth brain. But sometimes smooth brain is where we need to be in order to just get it in the head. So here are our representations. We can also, we can write these with our skeletal structure, but we also, using these names, can abbreviate it, and often will abbreviate it as methyl ME, ethyl ET, propyl PR, butyl BU. And then there are 2 kind of variants of these that you should keep an eye out for. One of them is isopropyl. So if you see this, it has 1, 2, 3 carbons, but it's just not attached at the end of the chain. It's attached in the middle of the chain. And so this is called an isopropyl. Iso because it's like equal prefix. But I like to think it's isopropyl after Y-sopropyl because it looks like a Y. Isopropyl, Y-sopropyl. The last one is we could have our butyl group as just 4 carbons in a line, or we could have all 4 carbons like this, where essentially they're connected to 1 central carbon, and it kind of looks like a chicken foot. This is what is called a tert butyl. And tert, it has to do with like this being a tertiary carbon, which is a little bit beyond y'all's pay grade right now, but y'all will talk about in a few lectures. So she is just the chicken foot. Like, I know it sounds basic, but I'm like, oh yeah, my chicken named Hurt. Like, you do what you can with the like straight up memorization. The other things like di, tri, tetra, like those are like prefixes that you can like use Greek things. Like, it's more intuitive, but these are just the memorization. So when we are naming a molecule, there are a few just key things that we have to do. First one is we need to find the parent chain, the longest continuous chain of carbons. Second thing that we need to do is we need to figure out which way to start numbering it. We can number it from like the left side of the chain or the right side of the chain, and we want to pick a numbering that minimizes the number on our substituents. So like if we had the option of having substituents with like 1, 2, and 6 versus like 3, 7, and 8 or something, we would want to choose this one because the numbers are smaller. Like essentially you would try out both options and just take whichever one is most compact. And then when you have substituents on your parent chain, you are going to list them in ABC order, and you're going to put the number carbon it's attached to as a locator. So let's do this process just to kind of see it all put together. So this exercise for practice 2 is they've given you the name of a structure, but it's a bad name. It's not the proper name for it. It's a name where we can use this and draw out like a structure that it is the one that they are talking about, but it's not this fancy IUPAC, which is like the standard chemical name that like the Chemistry Society agreed on all of the rules. So if we are given a name and we're trying to draw it, the first thing that we do is we look for our parent chain ending here. And here we have pentane. Now pentane, once we get past butyl, 4 carbons, 5, 6, 7, 8, 9, it follows predictable patterns of pentane, hexane, heptane, of these prefixes that you've seen in other contexts. So pentane, we have 5 carbons, 1, 2, 3, 4, 5. And now, since I'm drawing, I'm just going to start numbering this way. 1, 2, 3, 4, 5. If you are like given a structure and then you have to supply a name, that's when you need to test both sides. So we'll do that in a minute. Then we look at the substituents. So it says here on carbon 2, put a methyl. So in carbon 2, I'm just going to draw a line out. And remember, this line at the end of it is implied CH3. That's our methyl. Then the last part here in our substituents is 5-tert-butyl. So on this 5 position, we need to add our chicken foot. So with this, we've put kind of our 5-tert-butyl where we want it to be on the 5 position, the methyl where we want it to be on 2. But why is this not the right name? And the key here comes back to this first and most important part. Find the longest chain of carbons, the parent chain. And yes, there is a 5-carbon chain here, but then there's also 6 and 7. Like we have altogether 7 carbons as our longest chain. And so why would you call that a tert-butyl when she could be part of the parent chain? That's the idea here. So now that we have this, if we have a 7-carbon chain, our parent name is going to be heptane. Hept for 7. Then we look at our substituents now, and all of our substituents that we have are all going to be methyls, right? Like we have a CH3 here, CH3 here, CH3 here. So when you have multiple of the same substituent, you put a prefix in front of it. So that tells you how many there are. So because we have 3 methyls, we are going to call this trimethyl. And then we said that we had to list out locators for the position of each of these. So the first one is on 2, and the other 2 are on 6. And this might feel a little silly. We are going to write out 6 twice, just to be really explicit that 6 is the one that we have 2 on, that we have 2 methyls on, I should say. The thing is, if you wrote just 2,6 trimethyl, just from this notation, it's unclear if you have 2 methyls on the 2 carbon or on the 6 carbon, which is why we listed out when they are on the same carbon as like 6 and 6. So putting it together, the full IUPAC name is 2,6,6 trimethyl heptane. And like, let's say we had another substituent. Let's say we had a chlorine on 4. So that would be 4-chloro. The thing that we have to think about if we have another substituent is ABC order. What goes first? Well, for ABC order, this C in chloro would count. And the thing that's a little bit weird is when you have multiple of like methyls or ethyls, or when you have these prefixes like tri and everything, this actually doesn't count towards your ABC order. So you would still use M here for your ABC order. And so you would have 4-chloro first because it's first in ABC order with the C, and then you would have trimethyl with the M. And so that's kind of how you would do it with more substituents. Cool. Any questions on nomenclature before we move on to functional groups? Slide. So for functional groups, I am going to talk through some of them, but as I'm doing that, if you look at the practice 3, either on the handout or on the notes, go ahead and try to be circling any functional groups that you can spot while I'm like talking through it. And so like if I'm talking about something and then it pops up or you see it in the structure, go ahead and circle and name her. So functional groups essentially are our way of tagging molecules. They're our way of seeing that, oh, there's this like characteristic structural motif in a molecule, and it's going to tell us about how that molecule is going to react. And so to help you out with the sea of functional groups, I've kind of tried to provide some structure here and group them into some families. So first off is we have the hydrocarbons as families. So I put alkane in here, but alkane is actually technically not a functional group. Alkanes are really our standard of comparison. They're basic, plain carbon-hydrogen single bonds. They don't like to do a lot of reactions. But just because other names are kind of similar to alkane, I put that in here. But I'm going to kind of put it in parentheses as like, this is not technically a functional group, but it's the label that we use for if there are no more interesting things. If we have only carbon and hydrogen and only single bonds, it's an alkane. If we have a carbon-carbon double bond, we call it an alkene. And if we have a carbon-carbon triple bond, it's an alkyne. And the thing that I like to use to kind of remember this is from alkane to alkene to alkyne, going up 1, 2, 3 bonds, it's in ABC order here, which is a nice like little helpful thing. So alkyne having 3, and it's the furthest down in our ABC order. The other thing that we're going to put here is if we have like a benzene ring, and it can include other rings that have double bonds, but in this case you want it to have double bonds in every carbon in a ring, we call this an arene ring, and that's another functional group. So these are hydrocarbon family. They only have carbon and hydrogen, and really the only way that they can be interesting is by having double or triple bonds. Then we have the heteroatoms, otherwise called the oxygen mafia. So our quintessential member of the oxygen mafia is the alcohol. That is an OH on the molecule. And we have its cousin, the thiol. So this sulfur, like on the periodic table, you have oxygen, and right below it, you have sulfur. So they're going to react very similarly since they're in the same column and they're right next to each other. So we have the kind of sulfur version of the alcohol, which is the thiol. And you'll see thio as a prefix for a lot of sulfur things. Now, if we have an oxygen and we have carbons on either side of it, then we say it's an ether. So it's in the middle of a chain of carbons. And I don't think I explicitly listed this, but R here just stands for the rest of the molecule, the other things that we don't care about. R typically we can think of as being a carbon, some sort of carbon with the rest of the chain. And when I do a notation of like R or H, that means that we could have a carbon on the other side, we could have an H on that side, and whether or not we have a carbon or an H, it doesn't change the identity of the functional group. Whereas you'll see in a little bit, if we have some things on a certain side, then that will change the identity. So we have ether, oxygen with carbons on both sides, and we have the sulfur version of it as sulfide. Then we have, what if ethers got together and made a little throuple and made this little triangle structure? This now becomes an epoxide. And epoxides, even though they look like ethers, like this is attached to a carbon on one side, a carbon on the other side, because it forms the little triangle here that's really strained, it's going to react in different ways. So that's why we classify it as a different functional group entirely of an epoxide. The last one, kind of related to ethers, is if you have two ethers and they are attached to the same carbon, we call that an acetal. And again, it's just because they are going to react differently than just plain Jane ethers. And so if you saw something where there are two ethers attached to the same carbon and you circled it as ether, that would be wrong, because that does not tell us how this molecule is going to react. And that's a really common mistake I see people make, is just not clocking acetals. Now, if we have nitrogens that are attached to three things, and those three things could be carbons or hydrogens, we call it an amine. And if we have a halogen attached to a molecule, we call it an alkyl halide. So those are pretty straightforward. Then finally, the last family is the carbonyl compounds. So when we use the term carbonyl, carbonyl means a CO double bond. But really, it's not a functional group. Carbonyl is an umbrella term that includes all of these other different functional groups within it, but never, if we are asking for a functional group, never just put carbonyl, because it's not specific enough. So you won't get points with that. So if we have a carbonyl with carbons on both sides, it is called a ketone. And if we have a hydrogen on one of the sides instead, it's an aldehyde. My favorite way of thinking about this is ketones you can kind of bury in the middle of a molecule because it's carbons on both sides. But aldehydes, since one hide has to be a hydrogen, aldehydes can't hide. They are always going to be on the end of the molecule because they're going to have a hydrogen on one side. Then, if we have a carbonyl and we have an alcohol next to it, it's not going to be an alcohol and a carbonyl. And the reason is because there's resonance here. So there's going to be a resonance structure that looks like this. And because there's resonance, these two things react together. Like they react as one unit rather as being two separate things of a carbonyl and an alcohol. And so when we have a carbonyl with an alcohol next door, it's a carboxylic acid. And I've tried to kind of like lay these out sneaky of like, okay, then if we have a carbonyl and an ether, an oxygen attached to carbons on both sides, an ether and a carbonyl, that becomes an ester. And if we have a carbonyl and an amine, a nitrogen here, then that becomes an amide. And a carbonyl with a chlorine, that becomes an acid chloride. So I've tried to kind of like show some like patterns here between them. And the last one in here is the nitrile, and she's just a little bit weird. Like you won't know exactly why we include her in this family now, but she's a CN triple bond. And ooh, someone said some of these weren't mentioned in lecture slides. Which ones weren't mentioned in lecture slides? Because this could just be a thing of like me teaching it from another course. And I can try to bring it up really quick and see. Oh, I think acid chloride they didn't put on it. So, yes, you are not responsible for ones that are not in the lecture notes. I'm just used to them kind of introducing the acid chloride there. So that's the one that I'm seeing that's different. And then they also did put the nitro group. So if it's N double bond O, O minus plus, this is called a nitro group. And so maybe I'll put this in here as something that, again, feels kind of like carbonyl adjacent, but not exactly a carbonyl. Were there any other ones that looked like they didn't line up with lecture? Boop. Work. Cool. So, I'm hoping that y'all were doing some circling as we went with this. So let's go over what the answers to this are. So, I'll start off with the things that are not oxygens, because oxygens are a little weird. Here we have an SH, that's going to be our thiol, acting kind of like an alcohol. And then almost everything else has an oxygen attached. So, oh, actually, on the very end over here, we have our alkene, carbon-carbon double bond. Then let's look for auctions that are kind of boring or not connected to other things. So I have this OH over here. That's going to be our alcohol. But then all the other auctions seem to have some neighbors that we might need to take account for. So why don't we start with the carbonyls first? Here we have a carbonyl, and it's adjacent to this thing that looks like an ether. And so we said that carbonyls with an ether next to them are really called esters. And when you circle it, you are going to want to circle all of the atoms that would be necessary to call it an ester, which includes this auction over here, of like this is the neighbor here. Then at the bottom, we have a carbonyl. And with that, we have a nitrogen next door, and that's going to be our amide. It doesn't include the top carbon, or we just don't care. We don't care about this side. Like, you can circle it if you want, but like the thing that makes an ester is a carbonyl and one side's an oxygen. Yeah. And then last thing is over here, it looks like we have an ether, and it looks like we have another ether here, but the two ethers are connected at the same carbon. So that is going to be an acetal. Cool. Any questions on labeling these or the kind of distinctions of like, it looks like a carbonyl and an ether, but we actually want to give it this other name instead? Okay. Last thing is just, why do we use functional groups? So imagine I was telling you to like learn these reactions, and I could just generate a list of like 50 of these. And without functional groups, these would be like learning separate reactions for each one. Like each of these is a different molecule, so you could imagine this as a list of 50 different reactions. But if you have the language of functional groups, you could see that all of these are a reaction of a carboxylic acid and an alcohol coming together to make an ester. So that is a way that we can generalize molecules of, we don't care what all these R groups are. If we have these functional groups present, then they are going to combine and make this functional group. And so it's going to be really important once we start learning reactions, like in lecture 3, to have the functional groups kind of down pat. But with that, I'm going to keep on chugging just so we can try to cover as much as we can. So conformation analysis is all about how we look at molecules and how we represent them in our notation. And our two kind of big tools so far are perspective drawings and Newman projections. So firstly, perspective drawings. This is using wedges and dashes to talk about things coming out of the page or going into the page. So wedge means something is coming out of the page at you, and dash means it's going away from the page into you, away from you. So here, the bromine's coming towards you. Here, the nitrogen's going into the page. But we could just as easily write it like this. Like, these appear on first glance to be different because like one of them, the bromine's on the left side, one of them bromine's on the right side. But remember, wedge and dash don't mean left or right. No matter how we write it, the bromine is coming out of the page at you and the nitrogen's going away from you into the page. So both of those are fine. But if you swap the identity of what is on the wedge and dash, then it's different. So here in both cases, they were bromine. But that's our perspective drawing. And one thing that we are going to care about is how to turn this into a Newman projection. A Newman projection says, let's imagine we want to look at a molecule in a very specific way. And so we often will draw an eye and maybe an arrow that's saying, hey, we want to look at this molecule down this specific bond. And when we do that and we start to kind of build our Newman projection, it's helpful for me at least to think about this translating into the Newman projection in a few different stages. So firstly, the carbon that the eye first hits, I like to call the dot carbon, because on a full Newman projection, one of these carbons is represented as just the intersection of these three lines, so it's kind of like a dot in the middle. And then the second carbon is represented by a circle behind it. And so I would call this the dot carbon and the circle carbon, just to think, oh, okay, this dot carbon's closest to the eye, the circle carbon is a little bit further away. Then the second thing I'm looking for after identifying my dot carbon and circle carbon is when we have three substituents on the atom, it's either going to form a Y when we're looking at it, or it's going to form an upside down Y. And the thing that tells you which one is going to be is whatever is in the plane, the like straight line, that is going to be your like up or down part of the y. So like this or this. Over here, we see that our straight line thing is going down relative to where we're looking with our eye. And so that's telling me that we should have a normal looking y, where something goes straight down and then we have stuff to the right and left. And then the big challenge, and the thing that's kind of hard to see visually and get in your mind's eye, is if we are looking at the molecule from this direction and this bromine is coming out of the page, that is going to be on the right side of the eye. And I would highly recommend using a model kit and building this out just to kind of see that relationship, just because it's hard to imagine kind of like moving your head to the side and something coming out at you. And if you want in office hours, I can like talk through some more examples with that more explicitly. But you're imagining putting your perspective or the eye perspective here, and this bromine coming out of the page is going to be on the right side of that eye. And so that means that the nitrogen is going to be on the left side. Then we do the same exact process for this back carbon, the circle carbon. And here we see that our thing going straight up and down is going up. Like this methyl is going straight up. And so that's telling us that we have like a upside down Y shape. So our methyl is just going to be going straight up. And then we said the things that were on wedges were on the right side. So the fluorine is going to be on the right over here, and the OH is going to be on the left. Then we put together our dot carbon and circle carbon, and we get our Newman production. But all of this right or left, it depends on which side that we are looking at. If we instead had looked at this molecule from the eye looking over here, then here the wedges would be on the left side of our eye, and we would get a different looking Newman production. They are the same molecule. The Newman production is just showing a different view, a different angle that we are looking at it. So just getting comfortable with kind of working between those is going to require some practice. And again, I high key recommend, it's like $20 on Amazon, getting like a little model kit, because like it is going to be very crucial for seeing some of the 3D elements. And I think Serenia also talked about this for like, she said, bring your models to class on Thursday if you have them. There's just some terminology here. So we call like the specific way the molecule is sitting when we draw one of these a conformation. And it's just one of the like 3D arrangements of the molecules. And we can have two fundamental types of conformation. So one is like in the choir where everyone's kind of in between heads of the people on the row in front of them. So when they are all like having their own space and spaced out, this is called a staggered conformation. Or we could have them directly behind one another, which is, your choir teacher would be very mad. This is called the eclipsed conformation. And when we are drawing an eclipsed conformation, if we literally put this back line directly behind, it would be so hard to read. And so just notationally, we put it off to the side a little bit. But here, when they're like so close to the front carbon positions, then we consider this to be eclipsed. Then with this, we think about this idea of steric interactions. So if you have big, bulky groups, they're going to bump into each other. That's the fundamental idea behind steric clash. And so generally speaking, it's going to be more stable to keep your bulky things away from each other. So I have some more like specific information here with anti and gauche, just as kind of a review of like the terms that were used in lecture. But I think it would just be helpful to think about this Newman production here. Of this question is essentially doing something that I think is a little bit easier than building a Newman production, which is it gives you a Newman production and says, okay, give us the perspective drawing. Give us the like wedge and dash version of this. And there are like 6 or 7 different correct ways to do this. And I'm just going to show you one. And the way I'm going to show it to you, I'm also going to try to rely mostly on drawing tools rather than like 3D visualizing tools, just because I feel like that's a little bit different for everyone, like what works for them and what makes them be able to see it in their mind's eye. So for turning a Newman projection into a perspective drawing with wedges and dashes, I like to think about these images right here. So we know that this dot and circle means that we are looking directly down the line of a bond, but we can think about just tilting that slightly. And then this gives us a better idea of being able to see both the front carbon and the back carbon. So this is the looking at this bond dead on, and this is we're drawing that bond out just a little bit to be able to see it. So let's draw this first intermediate step, as we are just going to literally draw out that bond a little. So I'm going to draw it like a little wedge here. And this is going to be my back circle carbon, and this is going to be my front dot carbon. And on my front dot carbon over here, which maybe I'll do this in red, my dot carbon had a normal Y. So I'm just going to draw my normal Y. Okay. Then my back carbon over here, the circle, this one had an upside down Y. So over here I'm going to draw an upside down Y. And now all I did was just tilt it a little bit, and so everything's going to be in the same position. So on the back, the hydrogen's going to be up top, the other hydrogen's going to be on the left, and the ethyl is going to be on the right. And on the front, we are going to have the methyl on the right, the chlorine on the left, and the hydrogen down. So the last thing that we need to do to get this to a full perspective drawing is we need to just think about continuing this rotation around so that this bond, which is now kind of on the diagonal, we want it to be flat in the page. And the thing that I'm going to use to help me kind of trace this is thinking about the things that are straight up and straight down. So we have a straight up, we have our bond, and we have a straight down. So that should translate over here. So we want this hydrogen to be straight up, our bond, and this hydrogen to be straight down. Now, as we are doing this turn of the bond and making it kind of flat in the page, the thing that we want to think is, okay, what's going to start popping out of the page and coming towards us? Is it going to be the stuff on this side, side A, or this side, side B, if we are turning this bond into the page? Well, we can kind of see with this dragging, we're taking it away from us. We're pushing this further and further back. And so what that's going to mean is these ethyl and methyl are going to be going away from us. And then by virtue of spreading this out, these chlorine and hydrogen are going to be more towards us. So we are going to put the chlorine and hydrogen here on wedges coming towards us. And then we're going to put the ethyl and methyl on dashes going away from us. And with that, we have our Newman projection, our perspective drawing from our Newman projection. So again, I like this tool as an intermediate, as kind of like shifting between it. But I know that that's a lot, and especially with like a visual skill, it's a lot to kind of take in at once. I think the core thing that's helpful for me is thinking about these straight up and down and this bond that's between the dot and circle carbon as being your framework to put things on. And then you just have to answer the hard question of what to make dashes, what to make wedges. Because we're already over time and I want to make sure we touch on the last MO topic, I'm going to like keep on plowing through, and then I'll stick around for questions at the end and office hours and stuff. But the last part of this is just saying what would give us the most stable and least stable resonance structure. And to answer that, I said resonance, didn't I? The most stable and least stable Newman projection. So to answer that, we go back to thinking about these staggered and eclipse conformations. So the eclipse conformations puts the other like substituents on the back and the front carbon directly parallel to each other. And so that's going to have a lot of steric interactions. Like things are going to be hitting into each other. Versus staggered spreads things out. So we know that our highest energy conformations are going to be eclipsed, where they're bumping into each other. And our lowest energy ones are going to be staggered, where they're all kind of in these windows. So let me go ahead and draw that. And the way I'm going to do it is there are many different ways that you can draw the correct staggered and eclipsed conformations. I'm just going to keep the back carbon the exact same both times, and then I'm going to rotate the things on the front carbon. So I'm going to draw the exact same back carbon. And then for our most stable, I want it to be another staggered conformation like this, where we're all kind of, everyone's in their own windows. Versus for the least stable, I want everyone to be eclipsed, so right behind their front counterparts. There we go. So for our most stable, we want to put our two biggest things opposite each other. So our things that are not hydrogen here are, we have the ethyl, the methyl, and the chlorine. And our two biggest boys are the ethyl and the methyl. So if we are placing our ethyl here, we want our methyl to be exactly opposite it. So we are going to put the methyl over here. So we can imagine we just are turning the molecule to get it in this new conformation. And so when we turn our molecule here, the methyl goes in this position, but then our chlorine is going to be turned down to this position. So our chlorine goes down here. And then again, following that same line, the hydrogen gets moved up over here. So that is going to give us our most stable conformation. And for our least stable conformation, we want our biggest groups to be eclipsed with each other. So we said methyl and ethyl are our biggest. If our ethyl is here, we want our methyl to be right in front of it. So we are going to think about rotating this front carbon just by like 60 degrees here in order to make the methyl right in front of the ethyl. That means this hydrogen is going to go right in front of the other hydrogen. And then it means the chlorine is going to go right in front of this hydrogen. Woof. That's a lot. I will say, like, this is something that, like, it really is kind of a practice thing to get the hang of it, and it's also just something that's kind of frustrating. The Organic Chemistry as a Second Language books, I think, do a really, really good job of breaking this down step by step of, like, step 1, do this, step 2, do this, step 3, do this. But I'm also hoping that with the section videos, you're able to kind of go back and rewatch this process of breaking it down a piece at a time, even if right now it feels a little bit fast. With that, I'm going to plow on and do the most bare bones MO theory that I can that will be helpful for y'all. Sorry again for going over so much. This, I promise, won't be like a regular section thing. It is just there is so much content for the first lecture. So, last thing, MO theory. So molecular orbital theory takes us from the structure of atoms to whole molecules, and there are really only two big ideas that I need you to kind of take away from it. So the first one is the number of atomic orbitals that we have in our structure is going to be equal to our number of molecular orbitals. So hydrogen, she is all the way on row 1. She only has one atomic orbital, a single s orbital. But then all of our other major players like nitrogen, carbon, oxygen, all of those girls, they're on the second row. And so they have 4 atomic orbitals with like 1 s orbital and 3 p orbitals. And so we can kind of think mathematically about how many atomic orbitals that we have and like calculate them. So I'm going to start off with C6H6. C6H6, well, I have 6 carbons, and we know that carbon brings 4 atomic orbitals to the table. And then I have 6 hydrogens, and I know hydrogens bring 1 atomic orbital to the table. So if I multiply these out and add them, 6 times 4 is 24, 6 times 1 is 6, I have 30 total atomic orbitals for C6H6. And again, that's 4 for each of these carbons, and we have 6 of the carbons, so 24 there, and then 1 for the hydrogen. We have 6 hydrogens, so 6. So if we have 30 atomic orbitals, this tells us that we also have 30 molecular orbitals. And when we're building our MO diagrams, we'll see why that's important. So can you take a second and try it out for C3H7O, using that hydrogens only have 1 atomic orbital and all the other ones have 4. So here we have 7 hydrogens, each contributing 1. And we have 4 non-hydrogen elements. We have 3 carbons, 1 oxygen. And these are each contributing 4. So we do 7 times 1 plus 4 times 4. 4 times 4 is 16. 16 plus 7 is going to be 23 atomic orbitals. So we'll have 23 molecular orbitals. Evan, do you see where you got off with the 17?
Yes.
Work. Cool. So that's key idea number 1, number of atomic orbitals and number of molecular orbitals. Key idea number 2 is for every bonding molecular orbital, like any bond that we have, there's also this anti-bonding molecular orbital that's going to be empty. And it's kind of related to this idea in physics with waves. So when talking about waves interacting with each other, there's this idea that waves could interact in one way where it amplifies both the waves. It's called constructive interference, and it makes the waves bigger. That is like our bonding interaction, where these electrons, which we know from like Schrodinger, like quantum, whatever, electrons are partially like wave-like, partially particle-like. We don't need to know any of the math or any like other details, but it being partially wave-like kind of explains this phenomena of we have this bonding interaction, but also waves could overlap where like the peaks of one of them interact with the troughs of the other, and then they cancel out. And this is called destructive interference. And that's kind of akin to what our anti-bonding molecular orbital is. It's the out-of-phase overlap of our atomic orbitals. And so we did some drawing of molecular orbitals in lecture, and one thing that I wanted to flag, but I think I'll probably talk about it next time, is like when you have polar bonds, it's equal size on everything for the bonding and anti-bonding. But when you have, I'm so sorry, I said that exactly backwards. When you have a non-polar bond, like carbon-carbon, it's going to be equal size for both the bonding and the anti-bonding. Like all of these are the same size. But when you have a polar bond, like CO, you're going to get different shapes. The bonding one is going to have more of a like larger lobe on the more electronegative one, rather than like an even loaf. And the anti-bonding has larger lobes on the less electronegative atom. We're not going to do a ton with that right now. But with that, we can imagine like drawing all these orbitals. We have our sigma bonds and pi bonds. These are molecular orbitals, our kind of bread and butter. The last thing that we need to know how to do is to relate the energies of all of these. Yes, sorry. So with our energies, our sigma bonds are our lowest in energy. Then our pi bonds, we have our non-bonding orbitals or our atomic orbitals, like lone pairs, things like that. Then our anti-bonding orbitals, which we indicate an anti-bonding orbital with a little asterisk or a little star, so we'll call it pi star. And then sigma star is highest. We have this symmetry principle that the bonding interactions that are lowest in energy produce the anti-bonding interactions that are highest in energy. And so there's kind of this symmetric layout. And then within these buckets of energy, then we have a few different factors that affect what makes things lower in energy or higher in energy. So the big things are our CHs are going to be lowest in energy, then our CCs. And then carbons bonded to other things are going to be higher. And then we have to use things like, okay, if two atoms like CN are in the same row, and you are ranking like CN versus CO, you're going to be lower in energy if you have a smaller difference in electronegativity. If they are in the same column, like oxygen and sulfur in the same column, then the smallest difference in size, so like oxygen's closer in size to carbon, those are going to be lower in energy. To be honest, this is mostly here for a reference. Let's do a practice of the MO as our final thing, and then we will be done and we'll kind of see this in action. Again, sorry for it being so long. I will try to do this as quickly as possible. And if you need to peace out, peace out. Go with God. The last thing is they changed this molecule like earlier this afternoon. So the one I sent out in the PDF yesterday puts a chlorine here, but they actually want us to do it with a fluorine. And that's going to, I think, make it a little bit easier. So when we are building an MO diagram, we start with our Lewis structure. And it's helpful here to draw any lone pairs just so we can see them all. So the oxygen has 2 lone pairs, the fluorine has 3. Then let's count our valence electrons. So we have 2 carbons here. They each have 4 electrons. Then we have 3 hydrogens hidden on the end. So let's go ahead and draw them in. And hydrogen has 1 towards our valence electron count. So this is our carbons, this is our hydrogens. We have an oxygen, which has 6 towards our electron count. And then we have a fluorine that is going to have 7 towards our electron count. So adding all these up, we have 8 plus 3 plus 6 plus 7. So that's 10 and 14. So I'm getting 24. Is that what y'all are getting? Cool. So next up, we are going to count our number of atomic orbitals, what we were doing over here. So for all of the things that are not hydrogen, we have 1, 2, 3, 4 non-hydrogen things. So for our atomic orbitals, we have 4 non-hydrogen things, each of them contributing 4 atomic orbitals. And then we have 3 hydrogens, each contributing 1 atomic orbital. So in total, how many atomic orbitals do we have? Well, 16 and 3 is 19 atomic orbitals, which means that we should have 19 molecular orbitals. That okay so far? Cool. Once we've listed this out, this gives us our target number for listing out all the molecular orbitals, which is honestly the most common mistake students make, is they forget about orbitals. They just don't include them. And so by doing this little calculation at the top, it gives you your target number. So to list out our number, all of our molecular orbitals, we literally just look at the bonds first. So single bonds we know are sigma bonds. So we have a sigma carbon-fluorine bond. We have a sigma carbon-carbon bond. We have a sigma carbon-oxygen, and we have a pi carbon-oxygen with our double bond. And then we have 3 sigma carbon-hydrogen bonds. Does that look like it got all of our actual bonds listed on the page? 7 and 7. I think so. But then if our goal is 19 and we only have 7, we've obviously missed some molecular orbitals. So the first thing that we do after listing the bonds is we know for each bond we have an antibond. So we have a sigma star CF. We have a sigma star CC, sigma star CO, pi star CO, and 3 sigma star CH. Okay. So that gets us closer. Now we have 14, but 19 was our goal. So we're still missing 5. Any idea what these other 5 molecular orbitals should be? Feel free to unmute or type in the chat. Lone pairs. Lone pairs. Okay, so over here we have these 2 lone pairs. Those have to be in orbitals. So what we do is we list them as N for non-bonding. So N with a subscript O, that's a lone pair on oxygen. So 2 of those. And we have 3 lone pairs on fluorine. So N subscript F. And now we have all 19 of ours, so we're ready to go. And then for the question I got in the chat of why are there not 2 carbon-oxygen sigma bonds? It's because this double bonds are made up of 1 sigma bond and 1 pi bond. and that's just the makeup of a double bond. You can only have one sigma bond at a time. So now that we have all these, we put them in order based on their energy. So our sigmas go all the way at the bottom. Then we have our pi's. Then we have our non-bondings, our pi star, and our sigma star. And that's just the rough order of those energy buckets. But then we still have some work to do. We have to essentially put all these in the right order within the buckets. So this first step of just grouping them in the right order from these big energy buckets just comes from memorizing that sigma is lowest, then pi, then non-bonding, then pi star, and then sigma star. And so within the sigma bucket, let's start there, we know CH are lowest, then carbon-carbon, and then carbon something else. So we have our 3 sigma CHs, which I'm going to put this on our actual diagram here as lines to represent it. So I'm going to still keep this order, but I'm going to move it over to the side. And I start at the bottom. So I have 3 sigma CHs all the way at the bottom. And we said our next lowest is sigma CC. So we have these checked off. But then we have sigma CF and CO. So fluorine and oxygen, because they are in the same row of the periodic table, we're going to look at the electronegativity difference. And for reference, carbon is like 2.5, oxygen's like 3, and fluorine is like 4 for electronegativity. So who has the bigger electronegativity difference? Carbon-oxygen or carbon and fluorine? Well, in this case, 4 minus 2.5, that's a change in electronegativity of 1.5, and that's larger. And this is a change in electronegativity of 0.5, which is smaller. So the smaller change in electronegativity is lower in energy. So next we're going to have the sigma CO followed by the sigma CF. So that gets all of our sigmas. And that's really the only hard work that we have to do. The rest of it's going to be a lot easier. So within the pi bucket, we just have the pi CO. We don't have anything else. Then within the non-bonding bucket, we have oxygen and fluorine. And the thing that's going to determine the lower energy is just electronegativity. So the lower in electronegativity, the lower the energy is. So we're going to have our fluorines lower in energy than our oxygens, lone pairs. Then we have our pi star, which we don't have any ranking to do here. And then this top part, the sigma star, well, we already did the hard work with the sigma, and now we just need to do the symmetric inverse of this. So if the sigma CHs were the lowest, we know that the sigma star CHs are the highest. Then we have the sigma star CC, and then we have the sigma CO, so now we're sigma star CO. And then last we have our sigma star CF. So we have ranked the energy of all of our molecular orbitals. And the very, very last step is we populate our valence electrons. So we said we had 24, so we just start filling from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. With that, I'm sorry for the longest section I have ever gone over time. I appreciate you staying with me. I hope this was helpful seeing some of it. I am sticking around to answer questions because it is indeed office hours. But I promise we won't be going over so much in future things. Thank you for coming, and I will stop the recording and then see what questions you'll have.